Okay, thank you for watching this presentation. I'd like to begin by thanking my co-authors and advisors, Dr. Robert Braun and Dr. Hans-Peter Schaub. Also, if you're watching this after the live Q&A, please feel free to email me any questions or comments that you have. So with that, we'll get into today's topic, the prospects and challenges of AeroDrop, a method for co-delivering a probe and an orbiter via Aerocapture. Begin with an introduction. I'll go through the key prospects of AeroDrop, namely its advantages over other co-delivery architectures, and examining its applicability to some existing missions. We'll also go through the key challenges for AeroDrop's implementation, including an assessment of its feasibility, and then wrap up with conclusions and a live Q&A. So, by way of introduction, Smallsats, in particular CubeSats, have been increasing in both number and capability in the last couple of decades. They have transitioned from serving a primarily educational role to really making some significant scientific contributions. There's a variety of these smallsat science missions now under study. And in 2018, Marco, the twin CubeSat communication relays, flew to Mars with the Mars InSight lander and demonstrated successfully the potential of CubeSats as secondary ride-alongs on interplanetary missions. So this is a platform that has a huge potential for future planetary exploration missions. Also, there's Aerocapture. So Aerocapture is when you're arriving on a hyperbolic trajectory and you enter the atmosphere of a planet or moon and use aerodynamic forces to slow down and reduce your energy such that the vehicle, upon exiting the atmosphere, has captured into orbit and is on an elliptical trajectory, then raises its periapsis back out of the atmosphere, and this enables orbit insertion with a significantly less delta V than a purely propulsive orbit insertion. This idea has been around for a long time, but it has been often proposed and never implemented to date. Despite that, it has seen significant technological development and maturation over the years, and some renewed interest recently, in part due to the upcoming Planetary Science Decadal Survey and its expected focus on ice giants missions, which stand to benefit the most from Aerocapture compared to propulsive orbit insertion. There have also been recent studies on smallsat Aerocapture technologies, both at Earth and at interplanetary destinations. Finally, just defining a couple of key terms here. The entry flight path angle, or EFPA, is the angle between the local horizontal and the vehicle's planet relative velocity vector at atmospheric interface. And ballistic coefficient is the ratio between inertial and aerodynamic forces on the vehicle during hypersonic flight. So looking now at this dashed black box, we can zoom in and look at AeroDrop. So AeroDrop is the concept of a probe and an orbiter both arriving on the same approach trajectory and having identical entry conditions, namely their entry velocity and entry flight path angle are the same. And then one of the vehicles slows down much more through the atmosphere and its trajectory intersects the surface. We'll categorize that as a probe trajectory, where here probe is a catch-all term that includes landers, impactors, penetrators, etc. And the other vehicle slows down significantly less in the atmosphere, slowing down enough to capture into orbit, but not so much that it intersects the surface. So that's the Aerocapture trajectory, the orbiter trajectory. And so these two vehicles diverge in the atmosphere due to differences in their aerodynamic properties and can reach their desired final states from the same set of entry conditions. So having explained what AeroDrop is in a nutshell, why would it be useful compared to other techniques for delivering a probe and an orbiter to the same destination? Well, the first advantage I'll talk about is they can share a cruise stage. So the primary and secondary mission, the probe and orbiter, can share between them the power, navigation, communications, etc. And this means that the secondary doesn't have to duplicate all of this hardware itself. So using Marco as an example, it had its own solar panels, its own reflector array antennas, which took up a lot of its hardware. And on top of that, it had its own time required on the deep space network for its navigation to Mars. And so that is a significant resource constraint for a lot of missions. So if you can share DSN time between your primary and secondary mission, in addition to all this hardware, that's a significant benefit. AeroDrop also doesn't require any in-space propulsion for the probe. So to walk through this, if you're performing Aerocapture, well, if your probe and orbiter interorbit together and then the probe deorbits itself, it needs propulsion to perform that deorbit maneuver. Or if the probe and orbiter are approaching on the same trajectory, and then the probe diverts away from the orbiter to line up its entry conditions, then that divert maneuver would also require a propulsion subsystem. And finally, if the probe has a coast phase after an orbiter divert, but has these tight entry requirements, then the probe might require its own trajectory correction maneuvers. And to perform those, again, the probe would need a propulsion subsystem and other hardware and software for deep space navigation. So AeroDrop avoids all of these challenges because it doesn't require a divert maneuver. It doesn't need to be deorbited. It just has the same entry conditions as the orbiter, so it doesn't require its own propulsion subsystem. So again, if the probe and orbiter are coming in on the same approach trajectory but require different entry conditions, at least one of them must divert. And so if the orbiter is diverting, that divert maneuver being represented by this red triangle, well, if it's early, then the probe, which again has no propulsion subsystem, is then coasting all the way until entry. So its navigation error and uncertainty are increasing that entire time. And so this navigation error might exceed the required bounds at entry. So you can mitigate that by moving the orbiter divert maneuver later. Imagine moving the triangle to the right here. But then this orbiter divert maneuver inevitably will be executed imperfectly, and that may require a cleanup TCM afterwards prior to entry to get that navigation error back down. However, getting the navigation data to compute a navigation solution, design the TCM, and execute that TCM takes time, probably on the order of days. And so the later you push that divert maneuver, the less time you have to perform that maneuver. All that to say, executing a critical divert maneuver with your probe immediately before Aerocapture is a risky proposition, and AeroDrop can avoid that by eliminating the need for divert maneuver entirely. So in sort of in lieu of a literature review here, I'm just going through existing missions that have already implemented the probe and orbiter co-delivery using various architectures. But if you do know of a kind of holistic study looking at options for co-delivering probes and orbiters, please do let me know. That being said, we'll start with Viking. So Viking 1 and 2 both involved an orbiter and a lander getting its orbit around Mars together, and then the lander deorbiting itself after it's imaging the surface to check out possible potential landing sites and attempt to choose a clear landing site, clear of obstacles like Big Joe here. And this could still be required at destinations today, not Mars, because we have such good imaging capability there already. But even at unknown destinations, the technologies for aero maneuvering, hazard avoidance, terrain relative navigation have all advanced quite a bit since the 70s, likely not requiring this reconnaissance in advance. So if that were required, AeroDrop would not be a good solution, but it may not be required even for direct entry at destinations where we don't have a lot of imaging because of these technologies. Galileo and Cassini-Huygens are both famous examples of successfully implementing this probe and orbiter co-delivery. In this case, in both of these cases, the primary spacecraft released the probe and then diverted away. And amazingly, the probe then coasted without any course correction capability, in the case of Galileo, for nearly 150 days before entry at Jupiter, and still had a successful mission. In the case of Huygens, a 20-day coast. But you can see from these EFPA ranges that we see here that does sacrifice some delivery accuracy. So the EFPA uncertainty was quite a bit larger for Galileo and Huygens probes than it was for, as a rough point of comparison, the Mars Science Lab. So it got its delivery accuracy down by roughly an order of magnitude because it had that course correction capability all the way up until entry. So you can do a long probe coast phase, but you sacrifice that delivery accuracy. The Mars Microprobes were two small impactor probes that rode to Mars with the Mars Polar Lander, and are really a great example of the type of secondary ride-along architecture that we're looking for with AeroDrop. And AeroDrop could have a probe and orbiter that are of roughly equal size or importance, but it works best when one of the two is really secondary to the other. And that's partially because of this kind of logic flow I've diagrammed here, where assuming we have some primary mission and we know the entry conditions required for that, we can then determine the ballistic coefficient that would be required to achieve either a probe or orbiter trajectory from those entry conditions that are fixed, and then design a secondary secondary mission around that required ballistic coefficient, such that its capabilities and goals are determined after we know these constraints. And part of why this is easier for a secondary mission is that when you have a small mass and volume, it's easier to dramatically change the mass to area ratio than it would be with a larger vehicle. And lastly, I've already talked a good bit about MARCO. This was the carry-your-own relay architecture. And as opposed to the Mars Microprobes, which conducted their own science, MARCO provided this logistical support, which is absolutely something that AeroDrop would be enhancing for. In the case of MARCO, it's already taking advantage of these smallsat technologies. If you also applied smallsat Aerocapture technologies, you can imagine if MARCO had been able to capture into orbit around Mars using Aerocapture, and then it would have a longer useful mission duration, and could have also shared a cruise stage with the primary. So what then are some of the biggest challenges to implementation for AeroDrop? Just moving quickly through these, the separation event itself, the timing and size of that event. If it's too large, then you risk messing up the delivery accuracy you're going for, but if it's too small, you risk recontact in the atmosphere. The timing and observation geometry, you may have plasma blackout during hypersonic flight for both of the vehicles, and also the orbiter in particular is really constrained on its path through the atmosphere. So if you wanted to image an impactor event, that might be difficult for these reasons using AeroDrop. But if you wanted to do repeated flyovers of the crater left over from an impactor, that would be a great example of using AeroDrop. And then packaging and tight mass and volume constraints are really constraints of Aerocapture and Smallsats respectively, but both apply directly to AeroDrop as well. So I'll briefly walk through how we present the results of this feasibility assessment for AeroDrop. So we run a lot of simulations on this grid of ballistic coefficient and entry flight path angle. And if I choose a single ballistic coefficient, say 100 kilograms per meter squared, then over here at these steep entry trajectories, these are all lander trajectories, probes. But as I get shallower with my entry, eventually I lose quite a bit less energy in the atmospheric flight segment. And I have these Aerocapture trajectories that exit the atmosphere in a captured orbit. And then as I get even more shallow with my entry flight path angle, then I lose even less energy and I exit the atmosphere still on a hyperbolic trajectory, and those are escape trajectories. So these cutoff lines represent those transition points. And as AeroDrop requires the same entry conditions, we can see that what we're really looking at are vertical lines on these types of plots so that they have the same entry flight path angle. You can see here, anything below the black line would be a probe trajectory, and anything above it would be an Aerocapture trajectory. And so you can, on the same entry flight path angle, get those two different types of trajectories just by changing the ballistic coefficient. And I can get more out of this by assuming that I have some non-zero lift-to-drag ratio, and I fly, I just look at the bounding case and fly full lift up the entire way, then that's what this lower plot represents. And so now, I could imagine a probe that is full lift up and lives here on this -6 degree line. All of those ballistic coefficients are, an orbiter. All of these ballistic coefficients would then be orbiters, a full lift up trajectory, whereas all of the ballistic coefficients using a ballistic vehicle would be probe trajectories. And in the paper, we also annotate various quantities of interest, like the initial apoapsis here in blue, as well as peak heat rate and some other quantities that might also constrain your mission design. And so this case is just annotated with a nominal entry flight path angle, as well as plus or minus 0.5 degrees. And so you can see in this instance, a full lift up trajectory would need a ballistic coefficient of at least about 40, whereas to perform Aerocapture, whereas the ballistic vehicle performing a probe trajectory would need to keep its ballistic coefficient below about 150. And so the paper concludes results like that, also including full lift down results. So it's the full bounding cases for a given lift to drag ratio, results for Earth, as well as Mars, Venus, Titan, and Neptune. And AeroDrop is feasible at all 5 of those destinations to varying degrees that, again, you can see in the paper. But the most promising combination in general is a lift-modulated Aerocapture orbiter that's using a ballistic nominal probe trajectory. In particular, impactor and penetrator probes are the best fit because they're so simple. There are some limitations to these results, largely that we only consider one velocity at each destination, but we've shown that different velocities, while they change the contoured parameters, don't dramatically change the feasibility of AeroDrop itself. We also just use simple bounding cases to consider lift modulation and a really simple consideration of density uncertainty. But those in both cases are just to give a sense of how lift modulation or density uncertainty affect its feasibility in general, rather than to give really specific information. So with that, I'll take any questions. And yeah, thank you for watching.